to another statistical learning class. Of course, I got two materials today to accomplish, before going on spring break. I remember I walked you through this material on Wednesday on generalized linear model, but I think we still have, we started with all of that, and I actually need to walk you through estimation before, we go into the new material that I have. Okay, so I remember I introduced you to generalized linear model, like I said, okay, and of course, in the generalized linear model, okay, um, we use the idea of exponential family of distribution. We expect that the response variable should come from exponential family of distribution. The distribution of the response variable may not necessarily be normal. It could be other probability distribution, but those other distributions that we can accommodate should actually come from exponential family of distribution. And of course, this is if we can be able to show that a particular probability distribution can be written in this form that I'm showing right now, of course, an exponential family. So the other time, I remember if f of y is normal, okay, if f of y is normal, okay, so what I'm actually going to do first, I take the log of that, okay, the log, if I want to rewrite this, it's going to be 2 pi sigma squared raised to power minus half. The log that I'm taking, the log is a natural log of, I can rewrite this as this, y minus mu squared. Okay. Now, if you take a look, I can rewrite this as minus half log 2 pi sigma squared minus 1 over 2. That there's got to be y squared minus 2y mu plus mu squared. Okay. Now, if you take a look at what I have now, okay, you can actually in the picture, that I said ESP of y of that. So if I want to rewrite this, I can do this log 2 pi sigma squared, then here, okay, I'm actually going to have y squared over 2 sigma squared plus, okay, so y mu over sigma squared minus mu squared over 2 sigma squared. So if you take a look at what I have, so this is a log of fy. So if that guy is log of fy, if I want to go back to fy, I'm actually going to do ESP of the log of fy is the same thing as f of fy. If I have a log and I take the expectation, it's the same thing as that. So this guy now, I'm actually going to write exp. Okay. Now if I write ESP, okay. Now if you take a look at this, it's divided by sigma squared. Okay. That's why you see in the picture. And if you take a look at this guy as well, okay. So now if I want to write that, I can write y mu, okay, y mu, okay, minus, okay. So if you take a look at what I have, so this guy mu squared over 2, mu squared over 2. So all I can write that they're all divided by sigma squared. If you take a look at what I have here. Okay. Now, the rest, if you take a look at this, okay, I can actually rewrite that as negative half because here there's negative half. Here there's also negative half. Okay, so I can have as a negative half y over sigma squared, okay, plus log 2 pi sigma squared. So take a look at that. Okay, this and that. Now, if you if you take a look at what I have at the moment, then you're gonna see if you compare this with this, you're gonna see that if this is y, look at that, that's actually implies my theta to be equal to, mu. Okay, it's actually saying the theta equal to mu, and of course the b of theta, is mu squared over 2. Okay, the b of theta is mu squared over 2, as you can see right now, and the a of phi is sigma squared. Okay, the a of phi is sigma squared. Then the cy of phi is actually going to be this entity here. Okay, the negative that entity. Okay, y over sigma squared log 2 pi squared. Now, because of that, we said that normal distribution is a member of exponential family. Now, if it is a member of exponential family, okay, there's something I'm going to show you now. This is going to be the link function, because we needed for every distribution that is from that's a member of exponential family, we actually need a link function, a function that will link the random component to the systematic component. So right now, where I have x plus beta plus the error and the mean expected value of y equal to that. Now, this expected value of y here is a g of mu equal to that, and the g of mu that we have obtained is the mean itself, which is this guy here. So this is for normal distribution. Now, I will quickly go to any question on this? Any question on that? Okay. Now, I'm actually going to go. Are you done with this, right? Okay. Now, I'm going to go into another distribution now. So this is an identity link function. Okay. Now, I'm going to go into another distribution now. Now, if you take a look at this, that's a binomial distribution. Okay. Now, if you take a look at the binomial distribution is actually any question on this? Any question on that? Okay. Now, I'm actually gonna go. Are you done with this, right? Okay. Now, I'm gonna go into another distribution now. So this is an identity link function. Okay. Now, I'm gonna go into another distribution now. Now, if you take a look at this, that's a binomial distribution. Okay. Now, if you take a look at the binomial distribution is actually this, right? When y follow binomial distribution with n, parameter n, and pi is the probability of success. Okay, now I want to show that binomial distribution is a member of exponential family. Now, if it's a member of exponential family, then I will be able to derive the link function. Now, if this is a function, after taking the log, now if you take a look at this, if f of y equal n combination y, please pay attention. Pay attention. If I have this, and I want to, this is a binomial distribution, I want to investigate as a member of exponential family. I take the natural log. The natural log is going to be this. Taking the natural log. The log of a product is the sum of the log. Okay. Now, here I'm going to have log this plus y log pi plus n minus y log 1 minus pi. Then I simplify. Log this plus y log pi plus n multiplied by that. I'm actually going to have this guy minus this guy. Look at that. Algebra. Okay. Now, if I have this one now, okay, there's a y here, right? There's another y here, right? So if I want to rewrite, I'm going to write log n this, combining this and that. Okay, I'm actually going to have y. Log pi minus log that is going to be log pi over that. The law of logarithm. When you subtract the log, it's going to be log of the ratio of that. Now, plus n log 1 minus pi. Now, if this is a log, if I want to get my f of y back, I'm actually going to do ESP into log. The ESP, sorry, this is a log of f of y. So into f of y is now going to be ESP into log this, okay, plus y log that over that. And if I'm going to rewrite this in a exponential family form, okay, I'm going to start with this y log pi over 1 minus pi over 1 minus pi, this one first, plus n log 1 minus pi plus log this. If you take a look at this, I want you to compare this. Please pay attention. I want you to compare this. I want you to compare that with this guy. We want to compare with that now. Okay. So to compare that, why? It means this guy is the same thing as a theta. That is a link function. So it means theta equal log pi over 1 minus pi. Okay. And minus b of theta, as you can see, okay, the minus b of theta, you know, there's a minus here. Then it means your b of theta equal that. Okay. And automatically, your c of theta is going to be log. So your c of y alpha is going to be log this. And your a of phi is going to be 1. Or like divide. So your a of phi is going to be 1. Now, what we actually need is the link function. The link function is what we need, which is the log of the odd ratio. The link function is the log of the odd ratio. Now, the same thing with Poisson, but in Poisson distribution, the link function is log lambda. Log lambda. Now, in this class, I've shown you, three common members of exponential family. Okay, the normal, the binomial, and the Poisson. Okay. Now, if you have that, I'm quickly going to show you this. Please pay attention. Pay attention to this. Give me 1 second. Now, the other time, for normal, we derive the leaf function to be mu. That is what we're going to equate to the systematic component. For binomial, we derive the leaf function to be log of pi over 1 minus pi that we call the log of odd ratio that we also call the logit. That is what I'm going to equate to the systematic component. For Poisson, because I may be working with Poisson regression, okay, where the response variable is not continuous, it is not continuous, it is not categorical, but it is a count. There's going to be Poisson. And of course, we derive the logit to be the theta, the link function to be theta equal to log pi, okay, log lambda. And of course, the log lambda here now, the log lambda here now, okay, the log lambda that we have, it is equal to the theta, and in that case, our lambda is the mean. Of course, we know in Poisson distribution, the mean is lambda, and in the Poisson regression model, it's going to be log of lambda equal x beta, and lambda represent the expected value of y given us. Now, that is what we did on Wednesday. Now, how do we estimate parameters? The parameter is done by method of maximum likelihood. So the moment the response variable is from exponential family of distribution, the method of maximum likelihood estimation is going to be used, and the approach is going to benefit from asymptotic normality. Okay, so it's going to require getting the likelihood function first. Okay, we're going to get the likelihood function first, and after getting the likelihood function first, then we're going to find the log of the likelihood, and we're going to be differentiating, okay, with respect to the parameter. Okay, so the method of the numerical method is going to be used here because we're not going to have a closed form, okay, which I'm going to quickly. So we're going to do it in a way that until it converges, until the it is less than a certain threshold error value. Okay, now and after that we're going to have a second derivative. Getting the second derivative is we actually want to get what I call the Fisher information. The Fisher information is going to tell us the amount of information, the parameter, regression parameter carries about, the response. Okay, so take a look at that. And this is going to be the step. Numerically, we'll be able to estimate the parameter using the method of Newton-Raphson algorithm. Okay, so this is the approach until it converges. And the moment it converges, we can now obtain what I call the Fisher scoring algorithm. Okay, the Fisher scoring algorithm, then from there, the inverse of the Fisher scoring, what do you have inside Fisher information matrix? You have the second derivative. The inverse of that would be the Cramer-Rao variance, would be the variance. And don't forget, if I want to test hypothesis about parameter, or I want to construct a confidence interval, I actually need the covariance of the parameter. Okay, which is what you are seeing here. Okay, this is the testing. Okay, you know how you're going to test that. Okay, you've done stuff like that before. Now I quickly want to move to logistic regression and the goodness of faith for GLM.